we are going to start the second lecture on introduction to sets. In the previous lecture, we have studied the definition of objects and the sets. Then we have seen the representations using the set builder form and roster form. We have seen how the sets can be represented using these two forms. Then we have seen with an example that what we mean by well-defined sets. Then two notations we have introduced. One is the notation such that, and one is this notation belongs to. Then we have this introduction to some standard sets. We have introduced the set of natural numbers, and we were saying the set of natural numbers, it is denoted by n, and the set of whole numbers, it is denoted by w. After that, we have seen various examples of finite and infinite set. We were saying that if the process of counting it comes to an end, it is finite set, and if the process of counting it does not come to an end, when we are counting the elements, we are assigning the natural number to the elements, then that set, it is called infinite set. Then we are seeing empty set. Definition of empty set: the set which has no element. It can be represented with phi, or it can be. So we start this lecture with the definition of set of integers. The set of integers, it is denoted with z, and it consists of all natural numbers, the neutral number 0, and the negative of natural number. So if we represent them on the number line, these numbers 1, 2, 3, 4, so on, these are the natural number. These are also called the positive integers. Then these numbers -1, -2, -3, -4, these are the negative integers. These are the negatives of the natural numbers. Then 0 we have over here, this is the neutral number. This is the neutral number. So when we are talking about the set of integer, we are denoting it with z, and these are the elements of that set. So it is an infinite set. It has no least or the greatest element. Another important thing to note over here is when we are talking about these are the negative integers, -1, -2, -3, -4, these are the negative integers. So the remaining integers starting from 0 to 0, 1, 2, 3, 4, so on. These numbers, these are called the non-negative integers. So it is important to note over here that when we are talking about positive integers, we are saying these are the numbers 1, 2, 3, 4, and so on. When we are saying non-negative integers are 0, 1, 2, 3, 4, and so on. So 0 is included in non-negative integer, but 0 is not included in positive integers. Similarly, when we are talking about the non-positive, these are the positive from 1. So these integers 0, -1, -2, -3, -4, these are the non-positive integers. These are the non-positive integers. So if we look at the set of integers, they are closed under addition, subtraction, and multiplication. So what we mean by this is that if you will take any two integers a and b, suppose these are the two integers, these are from the set of integers. Then we are saying a plus b, it is an integer. A into b, it is an integer, and a minus b, it is an integer. This is what we mean by when we are saying closed under addition. Closed under addition means if we are considering two integers a and b, their sum is also an integer. Closed under subtraction, a minus b is an integer, a into b is an integer. Next we can see over here that if we have any equation of the form x plus a is equal to b, then where a and b, we are saying these are the integers, then this solution x, this is also n, then x will also belong to integers. X is also an integer. But if we are talking about the equations of this form, 2x is equal to 1, then the value of x we obtain 1 by 2, and this is not an integer. This is not an integer. It means that integers are not sufficient to solve these kind of equations. Now next we have is this example. A set A is given to us and it has elements x such that x satisfies two conditions. One is x is a natural number and x square minus 9 is 0. And second is the set B where we have the elements x is an integer and x square minus 9 is 0. So if we look at this condition over here, this condition I am talking about, it is same in both these cases. We are saying x square minus 9 is equal to 0. This is common condition in both these sets. So if we solve this, you will get x minus 3 into x plus 3, that is equal to 0. So this implies us x is equal to 3 or x is equal to minus 3. Now we come to the second conditions in both these cases. When we are talking about the set A, we have to write set A. We have additional condition over here that x can only be a natural number. And we can see that minus 3, it is not a natural number. So what we obtain, that minus 3 cannot be element of the set A. So the only element over here we have it is 3. Because of this additional condition that x can be a natural number, we are saying because minus 3 is not a natural number, so this element minus 3 cannot be the element of the set A. So we are saying that A is equal to 3. Similarly, when we are talking about the set B, we are saying the condition over here is x belongs to z, x is an integer. Both of these numbers 3 and minus 3 both are integers. So we can write the set B as minus 3 and 3. So what we obtain is that the set A is not equal to the set B. Both these sets, they are not equal to each other. Next is solve 5x is less than 24. Then two conditions are given, x belongs to n and x belongs to z. And in each case we have to represent the solution set on the number line. So when we are talking about 5x is less than 24, so this implies us that x is less than 24 by 5, that is equal to 4.8. So in the first case, plot the number line over here. We are talking about x belongs to n, so it is starting from 1, 2, 3, 4, 5. This 4.8 is somewhere over here. We are talking about the natural numbers 1, 2, 3, 4. So the only solutions that we will have, one is included over here. These dark dots, these are representing the solution sets. This is representing the solution set. So we are saying 4.1 is somewhere over here. It is not included over here. So the answer that we have, they are the points 1, 2, 3 and 4. We are saying the set, in the first case the set we obtained, it has elements 1, 2, 3 and 4. In the second case, if we plot the number line, we will have 0, minus 1, minus 2, minus 3 and so on. And then we will have 1, 2, 3, 4 and so on. Now we are talking about all integers less than 4.8. So integers less than 4.8 means we are talking about 4, 3, 2, 1, 0, minus 1, minus 2, minus 3 and so on. So the solution set we have in this case, it is so on up to minus 3, minus 2, minus 1, 0, 1, 2, 3 and 4. These are the elements in the solution set. Now we have already seen that when we are talking about the integers, they are closed under addition, subtraction and multiplication. So what operation we are left over here? It is the division. So let us look at some facts that when we are talking about the integers and how they interact through division. So to understand this thing, we have three terms over here that we need to understand. First is divisibility, second is factor, and third is the multiple. So to understand these terms, we start with the division lemma. So suppose there are two integers a and b, and it is given that b is greater than 0. There are two integers a and b is given to be greater than 0. Then division lemma says that there exists a unique integer q, that is called the quotient, and another integer r, that is called the remainder, such that a is equal to b q plus r, where this value of r, it is greater than equal to 0 and less than b. So suppose I am talking about 17 and 2. We will have 2, 8 is a 16, remainder is 1. So what we are saying over here, we have considered a is equal to 17, b is equal to 2. We have these two numbers. We are saying we have two integers a and b is greater than 0. Then there exists unique integers q and r. So in this case, the value of q that we obtain, we are saying 17 is equal to 2 into 8 plus 1. So the value of q in this case we obtain, it is 8, and the value of r that we obtain in this case, it is, this is the value of r, that is the remainder, it is 1. And clearly we can see that 0 is less than equal to r is less than 2. So this is the statement for the division lemma, that if two integers a and b are there, then there exists unique integers q and r. Q is called the quotient, r is called the remainder, and such that a is equal to b q plus r, and 0 is less than equal to r is less than b. Now the next term we have is it is the divisibility condition. So we are saying, again we are talking about the use of the division lemma. We are saying a number a is said to be divisible by another number b. As in the previous case, we were talking about a is equal to b q plus r. We are saying a and b are two integers, b is greater than 0. Then there exist q and r such that a is equal to b q plus r, and 0 is less than equal to r is less than b. Now we are talking about the particular case when this r is equal to 0. When this r is 0, we will obtain a is equal to b times q, that is when remainder is 0. And in this case, when the remainder is 0, in this case we will say that a is divisible by b. This thing is given over here. A number a is said to be divisible by another number b if dividing a by b leaves a remainder 0. If the remainder is 0, we will obtain a is equal to b times q for some integer q. So if we look at the example, suppose I am talking about a is equal to 16, b is equal to 2. So I can write 16 is equal to 2 into 8 plus 0. The value of q I have over here, it is 8. The remainder is 0. In the division lemma, in the statement of division lemma, we will have it in this form. So what we are saying, that 16 is divisible by 2. 16 is divisible by 2. And how we write this? If we are saying that a is divisible by 2, we can write it using this notation, that b divides a. How we read it? We are reading it as b divides a. We are talking about this condition. Or the number b is a factor or divisor of a. These are the terms we are using over here. Either we are saying b divides a, or we can say the number b is a factor or divisor of a. So these two terms we can use as interchangeable terms, or we can say the number a is a multiple of b. So we can use any of these three notations when we are talking about divisibility. We are saying that a is divisible by b, or we can write b divides a, or we can write b is a factor or divisor of a, or we can write the a is a multiple of b. Now when it is not divisible, we will put the cross over here. We are saying that 2 divides 16, 2 does not divide 17. These are just the notation. Another important thing to note over here is this same vertical bar we were using when we are talking about the such that symbol in sets. So whenever you are dealing with these kind of problems, if it is 2 bar 16 written over here, so it should be clear to you that in which context we are talking over here. So when we are talking about the integers, this symbol represents the divisibility. When we are talking in context to sets, this symbol will represent the such that. These are standard symbols. We cannot change these symbols at our own. So we have to check the divisibility of 28 and 29 by 7. So to check the divisibility of 28 by 7, we are writing 28, we can write it is 7 into 4 plus 0. The value of q that we have, that is 4, and the value of r that we have, it is 0. So what we obtain is that 7 divides 28. And when we are talking about the number 29, we can write it is 7 into 4 plus 1. Clearly this remainder we have, it is less than 7 and greater than 0. So the value of r that we have, it is not equal to 0. So we will say that 7 does not divide 29. So in this case we will say 7 does not divide 29. The next term we have, it is multiple. So we have already seen in our previous slide the definition. So again we are repeating over here. A multiple of a number is the product of that number and any integer. So in that case we are writing a is equal to b times q. So we were saying that a is a multiple of b. We are talking about, we were writing a is equal to b times q, where this q is some integer. So we are saying that a is a multiple of b. This thing will be more clear to you with this example. We are saying write the first 5 positive multiples of 5. So first positive multiple of 5, it is 5 itself. If we multiply it with 1, we will get it is 5 is a multiple of 5. Or what we are saying, 5 is divisible by 5. 5 into 2, 10. 5 is divisible by 10. This is the next multiple that we have. 5 into 3, 15. 5 divides 15. This is the next multiple. 5 into 4, 20. And 5 into 5, 25. So these are the first 5 positive multiples of 5. Multiple means that we are considering an integer, we are multiplying it with that number. Whatever number we have obtained over there, that is a multiple. Now the next we have is the term HCF. So HCF for 2 or more numbers is the largest number that divides all of them. So suppose I am talking about two numbers 18 and 24, and I want to find a largest number that divides both of them. Suppose I am talking about the number 2. 2 divides 18, 2 divides 24. If I am talking about the number 3, 3 divides 18, 3 divides 24. So I want to find the largest number which divides both of these numbers. So to find this, what we are going to do, we have listed the factors of 18. Factors of 18, they are 1, 2, 3, 6, 9 and 18. We have listed the factors of 24. They are 1, 2, 3, 4, 6, 8, 12 and 24. These are the factors of 24. Then we list the common factors. Common factor means when we are talking about factor, it is the number that divides both of them. Factor when we are talking about. So the common factors we have there 1, 2, 3, 6. And highest of all these common factors it is 6. So this is how we can calculate the highest common factor of 18 and 24. And this is the number, this is the largest number that divides both of them. Next term we have, it is the LCM. LCM is the smallest number that is divisible by both the numbers A and B. So when we are talking about the LCM of 4 and 5, we want to find the numbers that are divisible by both of them. If suppose I am talking about the number 20, it is divisible by 4, it is also divisible by 5. If I am talking about the number 40, it is divisible by 4, it is also divisible by 5. So I want to find the smallest number that is divisible by both of them. So again, we are writing the multiples of 4. Multiple of 4 are 4, 8, 12, 16, 20, 24, so on. We are writing the multiples of 5. They are 5, 10, 15, 20, 25, 30 and so on. Now if we write the common multiples over here, we will see that the common multiples we have there 20. The next common multiple we will have 40. Next we will have it is 60. Like this. These are the common multiples that we have. Then we have to write the least common multiple. So least value out of these it is 20. So we are saying that the LCM of 4 and 5 it is 20. And this is what the LCM is. That it is, if two numbers are given, it is the smallest number that is divisible by both the numbers, or if 4 numbers are given, then it is the number which is divisible by all 4 of them. Now next we have is the definition, prime numbers. So we are saying this is the property of the natural numbers. We are saying a number is said to be prime if it has exactly 2 factors. Exactly 2 factor means, if suppose I am talking about the number 2, the factors of this number 2, they are 1 and 2. If I am talking about the number 3, the factors of this number, they are 1 and 3. If I am talking about the number 4, the factors we have, they are 1, 2 and 4. If I am talking about the number 5, the factors I have 1 and 5. If I am talking about the number 6, factors I have, they are 1, 2, 3 and 6. If suppose I am talking about the number 1, the only factor I have it is 1. Look at these numbers. 2 has only 2 factors, 1 and that number itself. 3 has 2 factors, 1 and that number itself. 5 has 2 factors, 1 and that number itself. So these kind of numbers which have exactly 2 factors, this is important over here, they have exactly 2 factors, 1 and itself. These numbers, they are called the prime numbers. So we are saying 2, 3, 5, these numbers, these are the prime numbers. The numbers which have more than one prime factor, 4, it has 3 prime factors, it has 3 factors, not prime factors, we are talking about factors. We are saying 4 has 3 factors, this 6 has 4 factors. So these kind of numbers which have more than 2 factors, we are not saying which don't have 2 factors, we are saying which have more than 2 factors, it is strict condition over here. These numbers are called the composite number. So we are saying 4 and 6 out of this list, they are the composite number. 2, 3, 5, they are the prime numbers. Look at this number 1. It is not prime because for prime it should have exactly 2 factors, and for composite it should have more than 2 factors. So 1, we are saying it is neither prime nor composite. We are saying 1 is neither prime nor composite. And this is the condition why the definition is written in this form. We are saying a prime number is a natural number greater than 1 that has exactly 2 factors, 1 and itself. We have just included this over here so that it should always be clear to you that 1 is neither a prime number, 1 is neither a nor it is a composite number. Next we have is the fundamental theorem of arithmetic. So it says every integer greater than 1 can be expressed as a product of primes. If any integer a is given, we can always write it as a product of primes. It is p1 raised to the power alpha 1, p2 raised to the power alpha 2, so on up to pn raised to the power alpha n, where we are saying this p1, p2, so on up to pn, these are the primes, and these powers alpha 1, alpha 2, so on up to alpha n, these are the natural numbers. Then it is written over here, the factorization is unique, but for the order of factors, that the ordering of these factors, they can be changed. This will be more clear to you with an example. So we have to factorize the number. We have to factorize the number, or we have to find the prime factor of this number 60. So the prime factors, if we will calculate, we divide it with 2, we are left with 30. Then 2 is again the factor. Then we will obtain it as 15, then 3, and then 5. So what fundamental theorem of arithmetic says? That we can write this 60 as 2 raised to the power 2 into 3 into 5. This is how we can factorize this number 60. So like this, any number can be factorized. Now we are saying we can write it in this form, or we can write it as 3 into 2 raised to the power 2 into 5, or we are saying it is 5 into 3 into 2 raised to the power 2. This second statement, the factorization is unique, but for the order of the factor, it means that you can interchange the order of these terms, but the factors, the factorization, it is unique. That is, we have 2 raised to the power 2, then we have 3, and then we have it as 5. Factorization is unique. We can just change the order of the elements. Next are certain properties related to prime numbers. So we are saying let p be a prime number and a and b, they are the integers, and let n be the natural number. Then we have the following properties. The first property, it says that if p divides ab, then p divides a or p divides b. So suppose we are taking the value of p is equal to 5, the value of a and b we are taking 10 and 7. A is equal to 10, b is equal to 7. Then clearly ab we have it as 70. So 5 divides 70, then either p will divide a or p will divide b, or both will hold. So in this particular case, we are saying that p divides a holds. When we are putting or over here, it means either p will divide a or p will divide b, or both can hold. How both can hold? If suppose in place of 7, we are writing 70 over here. AB will be 700. So what we will obtain? 5 divides 700, then 5 divides 10, 5 divides 70, both these numbers. So this or just means this can hold, or both can hold. Similarly, if P divides a raised to the power n, suppose the value of P we have it is 3, the value of A we are saying it is 6, and the value of n we are saying it is 2. So what we obtain is, what we are talking over here is that 3 divides 6 raised to the power 2. Then this thing will mean that P divides 6, and this thing also implies that 3 raised to the power 2 divides 6 raised to the power 2. These are just the properties. You need not to cram this. These are just the properties that we will have, and we can use them at certain places. So you need not to cram all this. These will be used at certain places, and over there you can just refer to these properties. Next we have is another remark over here. We have listed the prime numbers from 1 to 100. Just give them a look. You need not to prime these numbers. Just look at these numbers. The prime numbers from 1 to 100, they are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89 and 97. So there are, how many primes are there from 1 to 100? There are total 25 primes. Next we have is write the following sets in set builder form. So the first set that is given to us, it has elements A is equal to -6, -4, -2, 0, 2, 4 and 6. So when we are talking about the set builder form, we are writing A is equal to X such that X has to satisfy some property. So what property X is satisfying over here? Look at these elements. These are basically these numbers, these are divisible by 2, or we are saying these are multiples of 2. It means we are saying X is equal to 2 times n. What are the possible values of n? The possible, where we are saying n belongs to Z, n is an integer, and -3 is less than equal to n is less than equal to 3. This is not the only way you can write. You can write in another way also, as you can find it comfortable to write. So this is one of the ways to write this set in the set builder form. We are saying it is X such that X satisfies certain properties. The properties in this case, they are X is equal to 2n. X is a natural integer. This n we are saying, not n. X, we are saying n is an integer and values lies over here. So if this set is given and we have to write this, what we are going to do? We are saying n is an integer. What are the possible values of n? This thing we can write n is equal to -3, -2, -1, 0, 1, 2 and 3. When you will substitute these values over here, the possible values of X you will obtain, they are -6, -4, -2, 0, 2, 4 and 6. And this is what the set A looks like. We have the elements of the A, they are in this form. Next we have the set B. Again we have to find some property which these elements they are satisfying. We are saying B is equal to X such that, now what property they are satisfying? If we look at this first element, it is 1 by 2. If I am writing it is n over n plus 1, and I will substitute n is equal to 1, the answer I will get it is 1 by 2. First element, it is satisfying this condition. Now you substitute n is equal to 2. When you will substitute n is equal to 2, the value you will obtain it is 2 by 3. But this value is not 2 by 3. It is not satisfied over here. So to look at this value, we can write 2 by 5, that is equal to 2 over 2 square plus 1. 3 by 10 we can write as 3 over 3 square plus 1. It means what properties this values they are satisfying. We are saying x is equal to n over n square plus 1, where the possible values of n, they are varying from 1 to 7. 1 is less than equal to n is less than equal to 7, and n belongs to the set of natural numbers. So this is how you can write this set in the set builder form. We are saying we have the elements x. X is satisfying certain properties, that x is of the form n over n square plus 1, where the possible values of n are 1 to 7 natural numbers. Next is the set C. It has elements 53, 59, 61, 67, 71, 73 and 79. Again we have to write it in the form, in the set builder form. So we have to see that what property these elements they are satisfying, what property these elements are satisfying. So look at this list: 53, 59, 61, 67, 71. So these are basically the prime numbers between 52 and 50. So how we are going to write the set C? We are saying it consists of all the elements x such that x is a prime number between 52 and 50. Or you can write x is a prime and 52 is less than equal to x is less than equal to 50. So you can use any of these methods to write this set. Next we have is a test to check whether a given number is a prime number or not. So suppose a number is given to us. Say I am talking about the number 29 and I have to check whether it is a prime number or not. So what we will have to do is, one method is, you start dividing. We know that 1 is always a factor of a number. Then we can clearly see that 2 does not divide 29, 3 does not divide 29, 4 does not divide 29, and you continue like this. You continue like this. We have to check all the numbers and then we can tell whether 29 is prime or not. Now another method we have over here is, consider this number 29 as n. Suppose n is equal to 29. Calculate the value of square root of n, some approximate value. If we will calculate the square root of n, we will get some value like 5.3. Say approximate value we have it is 5.3. We will list all the prime numbers less than 5.3. The prime numbers less than 5.3, they are 5, 3 and 5. These are the three prime numbers that we have, which are less than square root of 29. Now, we will check the divisibility of 29 with these three numbers. We are saying 2 does not divide 29, 3 does not divide 29, 5 does not divide 29. We need not to check with 4, 6, 7, 8. We need not to check it. We are just checking the divisibility of the number 29 with these three numbers. If 29 is not divisible by these three numbers, it means that the number 29 is prime. So in place of checking with all these numbers, this list is very large. In larger number, this list can be a very large list. But if we use this kind of result, we are using n is 29, we calculate square root of n 5.3, we just list the prime numbers less than square root of n, less than equal to square root of n, and we just check the divisibility with these numbers, and we can tell whether the given number is a prime number or not. Next term we have it is co-prime numbers. So co-prime is the property of two prime numbers when we are talking about. So suppose two numbers we are talking about, not prime, two numbers. So suppose there are two numbers given to us. Then we will say they are co-prime or we will say they are relatively prime if their greatest common divisor is 1, that is there is no common factor. Suppose I am talking about the number 8 and 15. 8 has factors 1, 2, 4, 8. It is a composite number. 15 has factors 1, 3, 5, 15. It is a composite number. But greatest common divisor of 8 and 15, that is equal to 1. So we will say 8 and 15, they are co-prime numbers. So both these numbers, these are co-prime numbers. Another term we have over here, it is twin primes. Twin primes is for two primes. Co-prime was not for the prime numbers. It is a property of any two numbers. When we are talking about the twin primes, we are saying two prime numbers, they are called twin prime if their difference is exactly 2. If I am talking about 3 and 5, both these numbers, they are prime. Their difference is 2. So this period is twin prime. 11 and 13, that both these numbers, they are prime number. Their difference is 2. So both these numbers, they are. This pair is called twin prime number. Suppose I am talking about the number, say 7 and 14. I am not talking about twin prime, I am talking about the co-prime numbers. Are these two numbers co-prime? You will say no, because when we are talking about the number 7, it has factors 1 and 7. 14 has factors 1, 7 and 14. The GCD of 7 and 14 is 7, which is not equal to 1. So 7 is prime, 14 is not prime, it is composite. We are saying 7 is prime, 14 is composite, but 7, 14 are not co-prime numbers. Suppose I am talking about 7 and 15. The GCD of 7 and 15 is 1. So 7, 15, 7 and 15, they are co-prime. 7 and 14, they are not co-prime. Another term we have is twin prime. Twin prime is two prime numbers are given and difference between them. 5 minus 3 is equal to 2. If the difference between them is 2, then those two prime numbers, they are called twin prime. 13 minus 11 is 2. So these kind of numbers, these are called the twin prime numbers. Now next we have is the Euclidean theorem, which states that the number of primes that we have, they are infinite. So to prove this result, suppose we are saying that we have, suppose we have finite number of primes. So if they are finite, it means the process of counting comes to an end. We are writing P1, P2, P3, so on up to Pn. These are the only primes that we have. The process of counting, it comes to an end. Now suppose we consider another number A, that is equal to P1 into P2 into P3, so on up to into Pn plus 1. This is the another number we are considering. Now is this number divisible by P1? We are saying P1 does not divide P1, P2, so on up to Pn plus 1. Why? Because by Euclid's division lemma, we have, if we divide P1 with this number, this is just like Q we have, but we are obtaining P1 into Q plus 1. So the remainder that is left over here, it is 1. So it is not divisible over here, because the definition of divisibility we have is the remainder should be 0. But in this case, the remainder we have it is 1. So we are saying P1 does not divide this number. P2 does not divide the number A. P3 does not divide the number A. So on Pn does not divide the number A. This is the number A we are talking about. And it is not divisible by any of the primes P1, P2, so on up to Pn. It means if these are the only primes that we have, we are saying we have a number which is not divisible by any of these primes. So what this thing means, that this number itself, it is a prime number and it is not the part of this set. So what we have supposed over here, that this set is finite, this is wrong. So we are saying that we cannot suppose that we have a finite set of prime numbers. So what we obtain is that the set of prime numbers is infinite set. We have obtained that the set of finite numbers, prime numbers, is infinite set.